Okay, so welcome to week 9 section. Today we're going to start by going over some stuff that we didn't get to do last week or the week before spring break on wake, and then we're going to talk about ordinal models and then the hierarchical models. If you remember, wake is a way of doing comparison between two models on the same data. And the metric that it uses is what is the probability or related to the probability that the model will do best in predicting out of sample. So that involves operations that are a little bit awkward to do in Stan while actually it can't be done while running Stan. You can either create an R function to do it with the MCMC output, or you could, if you need to use Stan functions, you could create a user-defined function that you can expose to R and then call that function afterward on the output. But basically there are two important parts to the wake calculation, and it has to be done for accumulating over all the observations in the data set. So the essence of it is this, and they also have to be done separately for each kind of model because it involves the likelihood and the log likelihood for particular observations. And so whenever your likelihood changes, you have to change your wake function a little bit. But so we're going to do for every row of the data, we're going to calculate a vector of linear predictors mu. So the intercept, if you have one, or you can just set it to 0, plus beta times that row of the X matrix. And so beta and sigma, when you pass them in, are going to be matrices equal to the number of draws that you keep from your MCMC output. And in the case of beta, it's going to have columns equal to the number of predictors that you had in your model. So it's conformable for multiplication with a row of X. So beta might be 8,000 by 6 or something. If you have 6 predictors and you have 8 chains and you keep 1,000 iterations per chain. So beta would be 8,000 by 6. You multiply it by a 6 by 1. You get 8,000 realizations of the linear predictor. And then you want to evaluate the log likelihood for the ith observation over the 8,000 draws of the posterior. So you're just passing to the normal density, the ith observation on y, which is just going to be a scalar, mu, which is going to be a vector of length 8,000, sigma, also a vector of length 8,000, and so LL will be 8,000 or however many draws from the posterior that you have, evaluations of the log likelihood for the ith observation. And then the components that go into the wake are the average of the log of the average of the likelihood. So we create LL with log equal true, and then E raised to the power of LL is going to be 8,000 realizations of the likelihood. The mean of that is the average of the likelihood for the ith observation over the whole posterior. And the log of that is what we keep adding to the first component of this thing out. And then the second component is just the variance of LL. So the variance of the log likelihood for the ith person over the posterior. And so we do that for all the observations in the data set. And then at the end, the second element of out is going to be the estimated effective number of parameters estimated. And then to create the first element of out, we have to do -2 times the difference between those two things that have accumulated up over the sample. And then it's going to return a value that has the wake, which is the thing that we compare across models, but it's also going to have an estimate for the effective number of parameters, which is just kind of a FYI because it's already included in the wake, but it's, you know, something that's kind of interesting on its own. And you can verify that you've hopefully written the wake function correctly if you get a reasonable answer for the effective number of parameters. It should be, you know, essentially equal to the nominal number of parameters if you don't have very much prior information, and it should be less than the nominal number of parameters if you do have a good bit of prior information. So if we want to just use this data set that we've been using a lot, the political economy risk, measuring the black market premium, we can do the model that we put up, you know, when we were first learning Stan. I'm not going to put it up again, but in any event, it's just a linear model with weekly informative priors for these data. And then we run it. And then the question is how to call the wake function that we've just defined. So it has arguments for y, x, the intercept if there is one, or it can just be included in beta, the posterior draws of beta, and the posterior draws of sigma. So I'm not sure if we've talked about this function specifically before, but the rstan package has an extract function, which is a little bit harder to use than it should be. But basically, you call that with the first argument being the object created by Stan, and then you can specify which parameters you want. In this case, beta. You can put a vector of strings indicating multiple parameters, in which case it's going to come back as a list. But if you only specify one parameter, then it comes back as a list of length 1. And to extract the actual matrix of it, you have to use the list indexing thing, even though there's only one element. So we extract beta. And so beta is going to be 8,000 by 13. I have 13 predictors in this case, inclusive of the intercept, and 8 chains, and keep 1,000 draws from each chain. So it just stacks all the chains up for you. And then I also need sigma, the posterior draws of sigma. And then in this case, because the X already includes a column of 1 and beta already includes realizations for the intercept, I can just call the function with intercept equal 0, pass it the y and the x that I had already made before, and you get a wake value of like 266 and effective number of parameters of about 12. When I did this previously, it came out 12.3, but yeah, it's a random thing because it depends on the draws from the posterior distribution. In any event, a value of about 12 or a little bit more makes sense because there are actually 14 nominal parameters, and I did put, you know, weekly informative priors on the coefficients, just like a Jeffreys prior on sigma. So that wouldn't help much, but you know, the prior on the betas was like independent, normal with mean 0 and standard deviation of 5. And so that resulted in having an effective number of parameters of about 12. Again, the effective number of parameters is the number of parameters that we would expect to yield the same variance in the log likelihood accumulated over the observation if we had that number of parameters but no prior information. So if you put prior information, then it reduces the variation in the log likelihood, and you get effective number of parameters less than the nominal number of parameters. So in isolation, wake is pretty useless. It's only a relative measure of how well the model is expected to do out of samples. So in order to use it, you have to estimate another model on the same data. So, you know, a lot of the coefficients that were estimated in the first model, you know, the 95% credible interval definitely includes 0 and all that. So we might think of a smaller model that just uses this measure of corruption, I think, to predict the log of the premium of the black market exchange rate. And so we can create a new X matrix, you know, the other stuff that we need, pass that to Stan and estimate a smaller model, post small, that has, you know, fewer parameters and stuff to estimate. Then we call wake again and give it the parameters that came from the second model. We get a wake of 258 and effective number of parameters of like 6 now. So if I can get these on the same, no, can't. In any event, 266 and 258. But again, this is on the log scale, so that's actually pretty substantial difference. If you remember from the McElreath reading, he shows how to calculate essentially weights that give the probability that a model among a fixed set of models will predict best out of sample. So you can put wake, which doesn't really have intuitive scale, into probability terms. And the formula for that is just e to the negative 1/2 times the difference between the you know, the wake of the model you're considering relative to the best wake, and then it's divided by, you know, e to the 1/2 of the, you know, the sum of all the differences. And so if we're just comparing two models, then there's only one subtraction to do. That gives you the numerator for the weight. The other piece of this is just going to be 258 minus 258, because that's the same model. So e to the 0 is 1. And so you can normalize this by dividing by w plus 1 in this case, because there's only two models. And then we can get the weights implied just from w and 1 minus w. And that basically tells us that we have 98.6 probability that the second model is going to be predicting out of sample better. So in this case, the model was estimated on 62 countries. And if we wanted to evaluate, you know, what would likely predict better for an additional country that was not part of the first 62, then, you know, by all probability, it would be the second model, which had fewer parameters. Yes.
So let's say it was something where you had weights of like 35 and 65 or 40, 60. When you're looking at those weights, does that mean you just essentially make a subjective judgment to the extent of, I think I'm going to go with what this model predicts because it has more weight? Or would there ever be a value in maybe trying to, in some way, assign the weights to the actual sort of estimations that each model gives you?
Right. So the models are different. They have different parameter spaces. So it wouldn't make sense to use these weights for a weighted average of posteriors. It is a good idea to use these weights for a weighted average of a posterior predictive distribution, or a function of the posterior predictive distribution, because that is a posterior prediction of observable y. And that observable y is the same for all the models being considered. So you have to estimate these on the same outcomes. And so it can be a good idea to do model averaging over posterior predictive distributions or functions thereof. It doesn't really make sense theoretically to do model averaging over posterior distributions because they have, this one had like 7 predictors and the other one had 14 or something like that. So it doesn't exactly make sense to average models that have different sample spaces to them. But that I think is, or at least to McElreath, preferable than saying, okay, here's a model out of like, 8 that has a plurality of the weight. So I'm just going to go with that one when, it's like 0.25, 0.22, 0.18. So it's not, in this case, it's pretty decisive, and any average you do would essentially be the same as just going with whatever model 2 says. But if you're estimating, a few different models and they, all have some weight, then it doesn't make sense to just take the one that maximizes this as being like the only model. That would be in effect giving a weight of 1 to the best model and a weight of 0 to everything else when you observe that, 0.25, 0.22, 0.17, something like that. So that's wake and the implied weights. Question?
I have a bit of a meta question, so you can skip over if it's
meta question.
It's just like on the question of it's just about like how we define one model versus another. Like, is the difference between the two models, structural? Is it about, one has a certain kind of parameter in it and the other doesn't? Or can it be as simple as, we assign this number to, the scale of that parameter in one and a different number to the scale of the parameter in another? Like,
so from a Bayesian perspective, everything in the STAN program is part of the model, even though it somewhat confusingly has a model block that I think we wish we named something different, but it's too late to do anything about it now. So you could have, same data, you have to have same data, but you could have same likelihood, different priors. You could have same priors, different likelihood, if probit versus logit, something like that. You could have different predictors. You could have, different inclusions of some interactions, but not others. So basically any difference is a difference in model. And you could use the wake to do. I think you should probably, specify the models that you are intending to do in advance before you start calculating wake or Bayes factor or anything like that. So you're not fishing as much. Certainly it doesn't quite seem right to, specify some priors, calculate a wake, it doesn't look so great, change your priors, something like that. But if you're, actually in an argument with a reviewer or something, and the essence of your disagreement is, that person has different priors about the parameters than you do. And, if you get into a situation where you don't think you can convince the reviewer to relent and you have to try to convince the editor to just ignore the reviewer, then, you could say that the reviewer has a 0.014 chance of being able to predict better out of sample than I do. So you should assign him 0.014 weight.
So like, I guess then the inverse of that question would be, what is common to, the thing that ties models together is basically a dependent variable?
Yeah.
Right? Okay.
Or variables in the case of a multivariate thing. But yes, they definitely can vary in what predictors they're using.
Sorry, a quick follow-up on what you were saying. So you wouldn't use the weighted average for posterior predictive distribution if the models you're using had different dependent variables in the multivariate case, would you?
Well, the wake is not applicable if they had different, neither Bayes factor, nothing really. If we're talking about, even if it's the same variable name, but you're using different n for whatever reason, then again, not comparable. And as we said last time, wake is also not appropriate if the number of parameters to estimate is increasing in the number of observations, because it's intended to be an approximation of leave one out cross validation. And if you do leave one, if you were to really do leave one out cross validation and leaving out an observation changes the number of parameters, then again, it's not really appropriate to do. Okay, so any other questions about wake? I didn't put an example of it, but it's very similar if you're considerations, if you're calculating Bayes factors. It's a little bit of a different metric. So the wake is the probability that one model or the others would predict best out of sample. The Bayes factor or the posterior odds is really what is the probability that one model is correct, relative to another model. And it's conceivable that a model is not correct, does a better job of predicting out of sample. Bayes factor is a lot harder to calculate because you have to approximate an integral. So there's some different ways of doing that, but it's not as easy as wake. But in any event, you could get a posterior probability for a given set of models using Bayes factor. You just also have to have a prior probability on those set of models, which is usually just 1 over the number of models, but could be something different. So moving now to ordered probit models that we talked about on Tuesday. So MCMC PAC has an ordered probit model called MCMC O-probit that's mostly a Gibbs sampler. It does data augmentation by drawing the latent utility, even though it doesn't store that for you. But it does other stuff because there's no closed form full conditional distribution for the cut points, which we called gamma on Tuesday. So it has to do something a little bit different within a Gibbs sampler in order to update its draws for those. And that is kind of the Achilles heel of it. We saw that there was only 2 possible values for the outcome, that the MCMC probit did really well in terms of efficiency, basically about as efficient as a markup chain could possibly be. And in this case, it's not so much. So there's, if we just use the same data set, but now we're modeling the extent of corruption, which is some ordered thing with like 6 categories, as a function of whether the country has an independent court system and the log of its GDP per capita or its wages per capita, something. In any event, you just sort of specify your formula, tell it your data set, and a couple other things. So by default, it does a method for dealing with the cut points that was written in a paper by Kate Cowles. And so that's the default way of calling this if you didn't specify it explicitly. There's a different way of doing it that was based on a paper by 2 guys, Albert and Chib. And you could also do a Metropolis Hastings thing to update the gamma, or in the case of Metropolis Hastings, there'd be some probability that you actually keep it the same for consecutive observations. And so we're just going to do the same model, same data set with the 3 different ways of updating the gammas. Remember, with MCMC, you have to give it different seeds when you call it with multiple chains. So I just draw a seed randomly in R and then pass it over. And then we can compare the efficiency or lack thereof of these different three ways of estimating ordered probit model. So if we look at the first one using the cows updating method, we get a dependence plot that looks like this, which perhaps looks not so bad. Shrink. No. Can you see it on yours? All right. In any event, it's there's not that much dependence overall, even at one lag. So that, you know, anything less than 0.2 for one lag is pretty good, but it dissipates very slowly. So green is 4 lags, blue is 9 lags, light blue is 16 lags, purple is 25 lags, yellow and gray, you know, maybe it starts to get close to 0, but those are 36 and 49 lags. So it didn't have that much dependence to begin with, but it doesn't go away really quickly. And what, you know, we need in a plot like this is to see the lag length at which it gets close to 0, stays close to 0 the whole post burn-in period. That way we have a value that we could do a test of a null hypothesis that the chains all have the same distribution. And it looks, in this case, that it would be like 50, at least. So that is not atypical for a Gibbs sampler, particularly if it's one of these like combination Gibbs sampler when I do know the full conditional distributions and something else when I can't figure out the full conditional distributions. But not super great. But you know, this sort of thing, or maybe even a worse sort of thing, is why people, when they think about doing Gibbs samplers, they're thinking, you know, tens of thousands or hundreds of thousands of iterations, because the dependence is so great and the effective sample size. In this case, you would get an effective sample size that looks pretty good because, you know, all of these are not so far from 0. But if you wanted to test the null hypothesis that the chains have the same distribution, you need to be thinning to like 50. If we look at the Albert and Chib method, might be a little bit better, but still looking, you know, 40, 50 lags before the draws become independent of another draw on the same chain. And the Metropolis Hastings one, you know, it looks okay. It kind of takes off at the end, but again, need a lot of lags to do the test. So if we just kind of say 50 for all of them, we could do the test here. We would reject the null hypothesis. We have a p-value of 0.03 on the interaction between the chain and the split. So not all 16 of the half chains have the same distribution. For the Albert and Chib method, we, you know, barely failed to reject the null hypothesis that they have the same distribution maybe. And, you know, also for the Metropolis Hastings one, we might barely fail to reject it. Depends on what p-value threshold you use. But in any event, the point of this was that it probably took about 50 lags to get a reasonable assessment of whether this chains converge. And, you know, if you have to thin by 50, then you need something like 10,000 iterations that you keep in order to have 200 that you can test. You know, if we only did 1,000 and we thinned by 50, then we'd only have 20 and only have 10 in each half chain. So that wouldn't work so good. All right. So, you know, maybe the Albert and Chib method, we think it's converged. How will we calculate the wake in this case? Well, we need to create a new wake function that is appropriate for the ordered probit likelihood. This is a little bit more involved, but it's the same deal. And one of the reasons why it's a little bit more involved is that MCMC OProbit follows what I believe is the Stata convention of estimating the intercept, but one fewer cut point. So it makes the first cut point equal to 0 and estimates the intercept. Whereas I think R and others will usually not estimate the intercept, but estimate one more of the cut points. So in any event, it's the same deal. We're going to loop over the rows of the data set. We'll construct eta, the linear predictor, for, in this case, it would be 80,000 draws or something like that. Yeah, so when doing the wake or when doing anything afterwards, you don't thin. The thinning business was just for the test. You can thin in MCMC pack at the outset, like if you have to do 1 million iterations or whatever, and you have a lot of parameters and you just can't store all that, but you know that the dependence is going to be huge, even out to like 1,000 lags or whatever, then you could thin from the outside. But in any event, we don't thin inside wake. So this eta is going to be like 80,000 by 1 or something. So when I call, just to skip ahead, to make this a little bit easier for me to do, so if I look at the column names of the output, the first 3 are coefficients, and then they have gamma 2, gamma 3, gamma 4, gamma 5, implicitly setting gamma 1 equal to 0. So when I create gamma, I'm just going to add an additional column on the left that's always 0. And so then in the actual wake part of it, so if the y, and I pass in y in integer form, just so I don't have to deal with the words, but I'm not doing anything with those numbers other than using them as labels, so it's okay. So if yi is the first category, then we want to evaluate the normal CDF at the first cut point, which is just going to be fixed to 0. So all the area to the left of the normal curve for that has a mean of eta. So this is the way that I like to think about it, but that would be equivalent to evaluating the area to the left of the standard normal distribution evaluated at first cut point minus eta due to the scale location business. So that's really what pnorm does on the inside anyway, but some software inclusive of Stan or whatever, it just has the standard normal CDF. So if you need to use it, you just need to subtract the mean from whatever it is and divide by the standard deviation. But here, standard deviation is fixed to 1 for identification reasons. So that's what we do if the person answers in the first category. If the person answers in the last category, then it's just 1 minus the CDF from the last cut point. And if the person answers one of the middle categories, then it's going to be the difference of 2 CDF values. So the cut point back, and then the 1 fewer the cut point 1 less back, leaving an interval of probability that you answer in category I. So we take that difference in regular probability and then the logarithm of that to be a log probability. Then we do the same business in terms of accumulating this up. And then, we get the betas, we get the gammas, we have our X, we put Y in integer format, so you can use the as integer function to do that. You also need to use the as integer function a lot when you're using stan, because stan doesn't take words, only integers. In any event, you can calculate the wake, and you get effective number of parameters of about 8, which because we didn't use any prior information and there was 8 parameters to estimate, that makes sense. And so if we had a couple models, we could compare the wake values of them, or even more than 2. So finally, before I let Rob talk, how would we do an ordered logit model? So MCMC Pack doesn't have ordered logit option because it's not possible to implement a Gibbs sampler for a ordered logit. Getting the full conditional distributions to come out in closed form is a particularity of normal CDF with normal priors and all that. So if we want to do it in stan, it's relatively easy. We're going to use the stan convention of not estimating the intercept, but we will estimate one more of the cut points. And there is a function for that in the zip file for today. And so it starts off pretty much like we always start off. Number of observations, number of predictors, a matrix. In this case, the matrix is excluding a constant. And we have to pass in an integer vector, integer array of length n that has the categories that everybody responded. We're going to declare a vector of betas, coefficients, k of them, and then cut points 1 less than the number of categories to chop up the logistic distribution. And then it's pretty much the same deal. The ordered logistic function in stan, unfortunately, it doesn't allow you to just pass in the whole data set. You have to loop over it to accumulate it up. So the fastest way to do that is actually make the ith value of the log likelihood, assign that from the ordered logistic log function, and to that you pass the ith response, the ith linear predictor, and the cut points. So this handles the mathematical manipulations and whatnot to get the probability of being in that category, and then the logarithm of that. And then you increment your log posterior by that whole vector. And then you could and probably should put priors on at least the betas. But, that's up to you. And then we can run that model. And then we see a dependence plot that is much more characteristic of stan. The previous ones for MCMC Pack excluded the burn-in because it doesn't save that. Stan will. So this is during the time it's converging, flattens out pretty well around 0.2 for 1 lag, and even 2 lags. So now green corresponds to 2. It gets close to 0, stays close to 0. It probably would converge to 2, but I put in 4. And we failed to reject the null hypothesis that all 8 chains have the same distribution. So this is an example where, stan actually gets more computational efficiency than a Gibbs sampler, or a Gibbs sampler with like 1 non-Gibbs sampler piece to it. And so that's really all it takes to slow a Gibbs sampler down, is just one thing, that it doesn't know the full conditional distribution. It doesn't move the cut points real fast or real far. And then all the full conditional distributions of the utility are conditional on the cut points. And so if it can't move the cut points very far, it can't move the utilities very far. If it can't move the utilities very far, it can't move the betas very far. So it takes 10,000 iterations or whatever, maybe even more, to do this, whereas stan just pretty much works fine with the default stuff. Okay, so that's it for me. Rob, who was a QMSS student and graduated last year, is going to tell us about hierarchical models. Do you need to email me any stuff, or you already did?
Yeah.
Okay.
It's the most recent email.
Most recent email. All right. Email from Rob. Disregard last email. Okay. So let's save this all. I'll put this on Courseworks afterwards, or maybe while Rob's talking. Let's see.
I hope you guys will be able to run the examples that I'm going to run. It's sort of kind of interactive. A lot of the talk's going to be just sort of using shiny sand. Ben tells me you guys know what that is, so it'd be good to get some practice.
All right.
So where is was that in Ben's?
No, not yet. I'll put it up afterwards. Unzip Rob and PDF. And it to be good. All right. That's not so good. Still, let me scoot the screen over. No, VGA is that screen. That needs to go right.
Yeah, it's perfect.
I don't know about that.
Is it possible to have R open, like
Yeah.
for the top?
Almost.
Well, if you don't zoom in, I think that might be okay. That's perfect.
Yeah. Okay. So just that's the PDF, and then our studio is in the other tab.
Oh, okay. And how do I get data? Is that just
What? So you need? Was there a .r file in there?
yeah? There's a couple of the like meetup code.
Okay. Yeah. So it's in the right directory. Just open it up.
And if I source from like oh no,
Did you?
Is this the where is this the most recent email? There was
Yes.
There's the one that says disregard.
Disregard last email. Yeah, I got that one.
Okay, let me see this one. Okay, well, this is okay.
Yeah. So in our
Yeah.
studio, that's where you want to be.
Yeah. Sorry about this. And if I just like it's in the right direction,
Yeah,
so I can just
it's
do that.
yeah. You're
Okay.
centered in the
Awesome.
working directory.
Awesome. Okay.
Okay, here we go.
So as Ben said, I'm Rob. No, sorry. I'm Rob. I was Ben's student a year ago, and I work on the Stan team now as a developer.
Where's your shirt?
I actually haven't gotten a shirt yet, so I think that means they like
We're redesigning the shirts. We had a new logo, and we had to get Microsoft's approval to use their font. It's taking a little while.
This is what everybody tells me, but I sort of get the sense that they might not want to keep me around for very much longer.
There's your names there.
You're right. That's because I put it up there. So
No, it's on the website.
I'm kidding. So yeah, I've been with Stan for about 5 months, and we're going strong. So just a quick outline. I'm going to try to get through as much as I can. There's probably too much here. This is a typical problem. So we're just going to define a problem and a question. We have data. We think that we can answer the question with the data. Pretty standard. We're going to formalize our question with a statistical model. We'll write the Stan model, analyze in ShinyStan, and then we're just going to sort of hack at the model and iterate until we like the output that we see in ShinyStan. So it's a very simple problem. Let's just say we have measurements for 100 stores from like a big box retail chain. All stores are in the US, and we have daily sales data. And the question we want to answer is how much can we expect to sell from a new store? Presumably someone wants to figure out if they want to spend the money to find a new location, open a new store. And so we have data that we think can help answer that question. So as we go about building fitting a model, and you guys, and feel free to just tell me like this is going too slow. I get the sense that you guys have probably coded hierarchical models in Stan before.
Stan models, we just started the hierarchical stuff this week.
Okay. So you have, no, okay. This is going to be good. Okay. So let's just say that we have, we have sales data by store by day. So we have 100 arrays of a bunch of different lengths, each with a single store's sales, and they're strictly positive. And so better organization, and this is not maybe not overall, but specifically to Stan right now, the way to sort of organize this data is to create a unified array of sales data, and you sort of just you iterate through these an array of arrays, and you stack the arrays on top of each other. But when you do that, you lose the information about what store each the sort of sales data came from. So you just have to keep track of how many arrays you've stacked, and you're matching sales data. Each data point gets a store ID, and you might think that there's like a natural hierarchy to the data. It's one chain. They're all in the US, so you'd expect probably sales to be correlated between stores, and so we want to maybe build that into the model.
So just to clarify something, there's no way to in R, one way you might think of getting around that problem would be you just like index subsetting or something like that, right? Is there a way that you can assign ID variables and like subset to indices?
Yeah. I mean, in Stan,
it's easier
probably
to extract than to assign. Yeah, it's not perfect the way you have to do it in Stan now, but Rob will show you.
Okay, so this actually will work. If you guys go to this URL, this has the one data set on it. I don't know if Ben, did you send the CourseWorks email?
No.
Okay.
I will. We'll put all this on CourseWorks, but you can get the data now.
And there should be one file. And we're going to go through and we're going to write the model. Does everybody have the data, or yes?
Put it in
no. Here, wait.
Directory.
I can go back. We can.
And just make a file in RStudio called.
So we're gonna fit a sort of a stupid simple model. You know, there's more in a real data set. You know, there would be a lot more structure probably. You might want to model sort of within store daily, you know, correlation in time. And you know, the data set that I generated doesn't have that that characteristic. But so we think maybe a good model for sales is just if we take the log of sales, you know, that'll give us numbers between minus infinity and infinity. And maybe those are normally distributed. And we think that there's probably some variation between stores. So we'll allow the model to fit one mean for every store that we have in the data set. And we also have to tell the model that we think that there is sort of within store variation. And that's that intra-store standard deviation. And I'm going to take everybody through the blocks. This is just sort of like a prep slide to, and definitely, Ben, if you think that I'm going too slow, let me know. So we got mean. So this is where the hierarchy comes in. Mean sales by store. We're going to put a distribution over that, and we're going to link everything together at the sort of top level with this mean sales across stores. And we're going to say that the standard deviation between the sort of the mean sales by store is this inter-store standard deviation. And then we're going to put like sort of default priors on all of the parameters aside from the hierarchical and the likelihood, which would be the log sales. So this is stuff that you guys know very well. We won't go through this. And is there any way to send the email now, or is it not so much?
Yeah, just roll on.
Okay. Well, all right.
Type real fast.
Yeah. I'm going to have this compile in the background because we have we got, this is the data block. We've got, you know, total stores, which is an you know, int with lower one, putting the constraints in the data block. We've got number of stores, which is the, you know, the total number of stores that we observe. We've got the sales by day by store. That's our Y, which we're going to take the log of. And that's, you know, that's a vector of length n of sales. And then we've got this store ID. It's an array of integers, and the array is of size n.
Although there's only 100 unique elements to it.
Yes.
Copy a bunch of times to fill it out to end.
Now we're going to go to the transform data block. We want to take the log of the sales, so we can do that within Stan, which is nice because it sort of elucidates what's going on with your model. So, you know, just very simply, we're going to loop over each of the data points, and we're going to take the log and assign it to a new vector of length n that's going to hold our log sales. Let's get this. Okay, so parameters block. We've got three sort of scalar parameters. We've got the inter-store standard deviation, the intra-store standard deviation, and the mean sales across stores. That's that hierarchical mean. And then we're going to have the sales by store. And that's going to be a vector of length 100. Now here's the model block. And what I'm going to do is I'm going to create a local variable called mean sales by obs. And that's just a way to sort of expand out the 100 entry mean vector into n length for the mean by observation. So I loop through my my store IDs, and as I'm looping through my store IDs, so I'm going 1 to n, I'm going to use entry I, which is just an integer, to index my mean sales by store, which is this length 100 vector. And I'm just going to assign that to mean sales by obs. And then I'm going to take, there's the log scales that are, the log sales, that's the likelihood line. And then we've got our priors down below where you can see here's that hierarchical structure coming in. And we're going to say that the stores are conditional on the mean sales across stores. They're exchangeable. And then if you remember, from long ago at the beginning of the talk, we wanted to figure out what the sales from a new store would be, and this is where we generate that data. This would be if if you were able to type really quickly and write the stand code. This is what you would run in R to fit the model. But I'll just do that up here. Okay. So that model is essentially just really naively translating between model and stand code. Here's the very familiar Shiny Stand interface. And so it looks like we're getting a standard deviation of around 10 for the intra-store standard deviation, and inter looks like it's around 1. And we always want to sort of figure out, and really these are the parameters we care about when we're deciding whether or not we want to make this new store. We want to figure out what the variance is between the means and what the variance within the stores are. So we should go to the posterior summary statistics, and this will show us R hats and effectives. And the thing that pops out at me is the fact that the inter-store standard deviation is awful. We have 4,000 draws, and we've got 24 effective samples. So that's bad. And we can, given that that's connected to, that is just a function of autocorrelation, we can see that this diagnose tab in Shiny Stand is really, really useful. And this is telling us that this, what we already know essentially, that this inter-store standard deviation, store standard deviation has a problem. This is actually not so bad, but if we look at mean sales across stores, that's no good. A lot of autocorrelation. Just a quick. Okay. So. Yeah, it's why this. I'm not going to be able to show the plot that I want it to. So one of the one of the sort of helpful things is to plot your parameters on the unconstrained scale. So you guys know that Stan's taking positives and mapping them to, minus infinity to infinity variables. So making scatter plots of draws on the unconstrained scale can sort of help you visualize what's going on as the sampler is jumping around. And so in order to do that, we need a log transformation of both the standard deviation things, but so if you did this plot, you'd see this like really ugly funnel shape. If you looked at you just picked a store I, you plotted that mean, and you plotted it against the log of the standard deviation, and you'd see this. And this presents problems for Stan, and you can just see why really quickly. I don't know if you guys remember the Hamiltonian Monte Carlo equations, but you've got your posterior, which is what we want to sample from. We're going to augment the parameter space with these momentum variables. We're going to sort of pretend that it's a physical system, and using some physics tricks, we can solve these two differential equations, and magically we get out draws for our parameters. And because they're differential equations, we gotta, and we're doing this on a computer, we've got to solve these discrete equations. And so this is key. We've got step size, we have a mass matrix, and we have parameters. And we're gonna iterate these. So we draw kinetic energy, which is these momentum variables. We're going to draw them from a bunch of normal 0, 1 draws. And then we take the gradient of essentially our posterior, and we update our momentum. And then when we're going to update our positions or our parameters, we're just going to multiply this vector that we've gotten from the last step. We're going to multiply it into the inverse of this mass matrix. And we're going to multiply each of the entries of the resultant vector by this single epsilon size. And we're going to update our equation. So, and then one very key step is after this is done, we're going to do Metropolis accept rejection step, and that's proportional to, it's essentially proportional to the error in how we solve these equations. So if this sort of approximation that we're doing for solving the differential equations is really good, that acceptance statistic is going to be pretty high. And if it's bad, it'll be low and we won't move very much. And if it's really low, this is where the autocorrelation comes from. Your sampler sort of gets stuck in an area. And what's happening is when Stan runs in warm up, what it's doing is it's trying to learn these two parameters such that these equations are sort of well approximated. But it only learns a single step size, and it learns a mass matrix that's fixed after warm up happens through to the end of the sampling. So you can imagine that if you have, if you've sort of explored this part of the parameter space in warm up, and you have this mass matrix is essentially the scale of your variables. So we've got a scale somewhere between there, and we've got a step size that was set out here. If we happen to jump into this funnel area, those step sizes and the curvature or the scales of the variables are wrong, and we approximate these differential equations really poorly. And right now in Stan, that's it. We can't really do much about it with sort of a fixed model. But what we can do is we can rewrite our model. We can do a couple things. We can, because it looks like the problems are occurring with the hierarchical standard deviation and the store level means, we can think about reparameterizing that distribution. That sort of mean of store I is normal with standard deviation, inter-store standard deviation. So we can do a location transform where it's just sort of a simple, we take a scalar mean cells across stores, and we add some normal random variable with mean 0 and standard deviation. We get out sort of the correctly distributed random variable. And the change to the Stan program is going to be we're going to add transform parameters. And you can see that we've got this new variable, perturbation from mean, which is added to the parameters block above. And we're going to add to perturbation from mean. We don't have mean cells by store in the list anymore. And then we're going to create this new thing. And we're going to sample from it. And given that we have like a minute left, I'm just going to tell you that it's still bad. We haven't fixed the problem. What ends up happening is we need this location scale transformation, where instead of just adding the mean, we're also we're going to take a normal random variable of mean 0 and standard deviation 1. We're going to multiply it by this inter-store standard deviation parameter, and we're going to add the mean cells across store. And that is essentially changing what this looks like. It turns it from this into this really nice sort of like big circular distribution, which is what we want. And I don't know if do you think we have time to compile the model and
I think
run it quickly?
No one in here next, so we'll just take like 2 more minutes.
Okay.
You gotta stop your shiny stand. Just do escape. That would stop your YouTube. Hit that. Just hit escape and yeah.
Okay. This is always the worst part of Stan, is like waiting for this to compile, but luckily it's not too bad here. So you can see the inferences that we get out, the mean, the distribution that we get out for the intra and inter-store standard deviations, and the mean look pretty similar. It's around 10 and 1. But when we look at the N effective for inter-store standard deviation, it's much better. And if we go to the diagnose tab, this is going to tell us that we don't have any problems. So that's great. This would be a good first step in answering this question that we have to answer. So the key takeaways are just that how you write the probability, really the priors for your model, makes a huge difference in the inferences that you get out. You should always run diagnostics. ShinyStan is awesome. Go to the diagnostics tab. Take what it says seriously. And we didn't have enough time for this, but that transformation doesn't always work. It's totally dependent on the process that generated your data. So what Ben will send you is going to include another data set, and you'll see that if you use location scale, you'll get out really bad. You'll get bad sort of draws, and that's just because this parameter space is constrained by the data you have, and if the data happens to push you to an area of the space that is good for one transformation and bad for another, you'll get these differences between models. And so you just sort of have to iterate, hack, iterate, see what comes out, and that's it.
Cool. So we'll cut this. Does anybody have any questions for Rob?